Hello to everyone, my name is Eva Russwurm. I'm working at University of Erlangen-Nuremberg at the Institute for Factory Automation and Production Systems, and my tasks are to simulate and to work for virtual commissioning. Today I want to show you my work on co-simulation of automated production plants based on plant simulation and using the Mechatronics Concept Designer MCD by using OPC UA. In my presentation, I will show you a co-simulation using OPC UA. And first, I will give you an overview about systems engineering and a co-simulation. What is a co-simulation? That is used for synchronization of different disciplines as software, mechanics, and electronics. For the IT infrastructure of my co-simulation, I use OPC UA, and at the end I will show you the project where I have an approach for doing virtual commissioning of a DC plant control. The systems engineering approach is undergoing constant change and is already being used in many companies as a part of product development. This approach, which offers many advantages in collaboration, efficiency, and product quality, as well as in cost, can meet the challenges which come out of Industry 4.0. Various tools are needed to implement systems engineering. You can use a PLM system for collaboration, but there is also the possibility to use other infrastructure as OPC UA communication standard. I will show you a combined form of co-simulation for the used disciplines, which I already told you. Nowadays, the automation of production systems is characterized by a high technical complexity and strong interdisciplinary. So the approach on the using of continuous engineering is useful applied to the development of mechatronic systems. The planning of an industrial plant requires the coordination and integration of various specialists from different disciplines such as mechanics and electrical engineering or software. They need to do the procedure and to get the best results. In this context, automation as a link ensures the correct interaction of the different disciplines. Due to Industry 4.0 approach and the associated increase in IT in the manufacturing industry, the relevance of digitalization of production is increasing significantly. This is already evident during product development because engineers from different disciplines already has to work together here as a part of systems engineering. The engineers and the process require a data platform that ensures data consistency and enables access as well as the possibility of exchange across all disciplines. The increasing complexity which arises in Industry 4.0, it arises from customer requirements. The customers need or they want to have a process flexibilization for the increasing individualization of products. And it's important that all plants in operation, they are working together in a big network in order to get a monitoring of production. This is why we need to work together, and not only together at the same place, but also together in a system or together using software and tools in order to make the process and the production plans better and good for our customers. Continuous engineering is developing into systems engineering and follows relevant principles. The three central elements of simultaneous engineering, they are parallelization, standardization, and integration. And these are all needed in order to get mechatronic products and mechatronic plants. The definition of mechatronics is synergetic interaction of the disciplines mechanical engineering, electrical engineering, and information technology in design and manufacturing of industrial products, as well as already in process design. Therefore, the engineers, they need cooperation interfaces in order to work together at one task. The consideration of interactions among each other due to the high number of interconnected elements is one of the most important points using continuous engineering in order to engineer mechatronic products. The three central elements, which I already mentioned, are important. Parallelization in this context means to optimize the timing of the sub-processes that are actually independent of each other and which can be processed independently. In standardization, the primary goal is to avoid duplication and repetition of work. This is primarily achieved through a specified uniform designs of modules, components, phases, and interfaces between projects and departments. The goal of integration is to turn interfaces into seams. That means to serve to bring together all product information in one part. This multidisciplinary structure of the model is based on an iterative procedure. Integration process and synchronization points are continuously checked, and they guarantee a successful product development due to early error prevention. Furthermore, valuable time can be saved through parallelization instead of sequential product development, which has a positive effect on a required time target, time to market. In order to meet this goal, certain methods such as reuse must be applied within the process of systems engineering. Consequently, the use of systems engineering to support the change of individual products must be considered as a solution. Regarding model-based systems engineering as a further development of systems engineering, simulations play a significant role right at the beginning of the development process. Simulation itself is the modeling of a system with its dynamic processes in a model that can be experimented in order to arrive at results that can be transferred to reality. So nowadays it's necessary to design an automated production system not only in part of mechanics, but also consider the entire mechatronic model to take into account interaction between modules and models, because it is a complex entity. So the complexity, which increases with the number of elements, needs to be brought together with links between the elements to regard every part, to regard every model, to regard every part of the mechatronic system. In order to make the complexity manageable, the system is divided into several levels. And in each level, relevant questions can be answered by using simulation. In the context of MBSE, model-based systems engineering, this means that individual components of the plant can be considered separately, but also that individual disciplines can be considered independently of each other. Thus, there are great opportunities for improvement in planning and operation of production systems in using simulation technologies. Multi-physical simulation programs are already available from various manufacturers that are predestinated for solving mechatronic requirements. Examples herefore are the Mechatronics Concept Designer MCD, iPhysics from Machineering, or Virtuos from ESG. These systems do not offer a not only offer a simulation environment, but also interfaces to use virtual commissioning. There are tools for mechanical and electromechanical simulation, manufacturing, tool and fixture design, quality inspection, and mechatronic concept development. In this context, geometries modeled in mechanical design can be extended to a simulation model that includes aspects of automation technology in addition to multi-physics-based simulation, thus visualizing the physical behavior of different solution concepts. Based on the model-based systems engineering and a cross-domain solution concept, the simulation tools promote early interdisciplinary collaboration between mechanics, electronics, and software. This is reflected in particular by cost savings and accelerated product development times. The aforementioned increasing degree of complexity of production systems makes it necessary to link additional simulation environments. To this end, distributed simulation has gained an importance in recent years. Initially, this involves a simulation model that is divided into different modules in the sense of different levels. Data flow exists between the individual submodels via databases which ensure data consistency. Digital product data in form of work plans, calculations, and CAD models are available in various database systems and can be used and modified by all those involved in the development process. The resulting product or product data models, which function both as interdisciplinary information carriers and as a link between the individual product development areas, such as planning and design, from the basis of distributed simulation. Distributed simulation is also referred to as co-simulation and can consist of partitioned simulation or tool coupling, as shown in the table. The aforementioned discipline-specific simulation solutions developed in the context of Digital Factory are very powerful in terms of mapping accuracy as well as computational performance. These are designed for the virtual mapping of selected processes. For a comprehensive modeling of the entire process, machine and plant behavior with all occurring interactions, high-resolution submodels of the most diverse simulation domains must be integrated into the digital image of the product plant and coupled in an overall simulation. Here, the overall simulation is in plant simulation. The context of multidisciplinary modeling of processing machines, a central problem is mentioned in the unification of models from different simulation disciplines into a multidisciplinary overall model. This is because the relevant data of the individual models must be provided via a neutral uniform data interface. Manufacturers of simulation software, meanwhile, confirm this thesis by integrating neutral data interfaces in every tool. A simulation tool is needed as a base that passes on the data of all individual simulation tools. For this purpose, there are various approaches and tests in diverse contexts, but no system that has become established. In the use case that I will show you, there you can see a co-simulation for the holistic simulation of a production plant operated with direct current, which I will demonstrate you. I used OPC UA as a communication standard in the field of automation. The goal is to develop more effectively, more cost effectively, more time effectively, and if possible, we would try to get the commissioning systems directly at the customer side ready for production in sense of first time right. Just as the need for standardization and modularization in the software landscape is becoming louder, there is an increased demand for standardized interfaces between several components at the communication level. In this context, OPC UA has emerged. OPC UA stands for Open Platform Communications and is a communication protocol that is used primarily in the context of Industry 4.0 and that enables standardized access to devices, machines, and other systems in industrial environment. It forms the interface between control systems and control level, enabling uniform data exchange regardless of the manufacturer or the tool. So I used OPC UA server in order to communicate between the different tools which are part of the co-simulation. With the help of the described OPC UA standard, the co-simulation for the automated production plant, which I will show you, was realized. The automated production plant is supplied with its own industrial level DC circuit with a voltage of 650 volt. Here, in addition to the multi-physical simulation of the process flow, the simulation of the power supply network plays a significant role. On this slide, you can see the mentioned production environment. Below, you see the multi-physics simulation of the process. The process is performed within the Mechatronics Concept Designer. The computing power for this process is also within the Mechatronics Concept Designer. Various aspects of the simulation are mapped in great detail, others less. Here, the process stages are recorded and stored in the OPC UA server. Specifically, the states are then passed to plant simulation. Here, the energy analysis is carried out. So you see the plant status signals are coming out of the Mechatronics Concept Designer, where the consumers, the soldering system, the conveyor belt, the robot are simulated, and the status signals are sent to plant simulation by using the OPC UA server. Using the energy modules, which are already available in plant simulation and which we have developed ourselves, the consumption of energy can be output directly and also related to the respective plant or to the consumer which needs the energy. Even if the model in plant simulation moves, it only moves into this state which is specified from the Mechatronics Concept Designer. So you get the state that the conveyor belt is running, and so the conveyor belt in plant simulation is running. A typical behavior for photovoltaics is also stored in plant simulation. It contains a typical year and typical days for summer and winter time and one average day during the year. And the data for the photovoltaics is stored in a table with change of the change of state is always carried out after 5 minutes. So every 5 minutes you get a new value or new data for the photovoltaics in plant simulation. Here, or in my case, we do the simulation always with an average day. The output power which comes out of the photovoltaics is stored in the accumulator. The behavior of the accumulator is also similar within plant simulation. We use different methods, therefore. So if a power peak in energy demand occurs in the process, this can be absorbed by taking power from the accumulator, and so an expensive purchase of energy from the supply network can be avoided. Whether the accumulator discharges or not, the state of accumulator is controlled by the connected controller. It's a PLC, and here to simulate the PLC, we use PLC Sim Advanced. So the PLC is defined in TIA Portal, and the project of the TIA Portal is loaded to PLC Sim Advanced to a virtual controller. And the virtual controller controls the behavior of the power supply for the whole plant. Why do we use a simulation of a production plant which is holistic, which uses different aspects? That's in order to integrate new renewable resources as well as storage technologies into automation production plants. So the smart grids can be established at the level of the production hall, and we want to control the plant's energy supply via one dedicated central control periphery in order to gain more advantages contra the power supplier. So the simulation of material flow and process in common tools of multiphysical simulation is done, and we only have to connect it to the electrical behavior. So the simulation of components of electrical engineering in tools of electrical engineering is done. The engineers, they know their tools, they can use it, and they have to be connected together in order to get all advantages. Earlier I mentioned that the simulation of the process is performed in Mechatronics Concept Designer. This means that the computing power for the simulation of the process is also required there and called up there. In a distributed simulation or co-simulation, the advantage is that not all processes are calculated and executed in one and one only tool, but that the load of the computing power can also be distributed to different tools and even, if needed, to different computers. In our present case, the server, the OPC UA server, has the greatest data load because the server must process or store or buffer all data. The controller, which controls both process and energy management, also has a high computing share. This could be changed to a distributed control periphery if wanted and if needed, so you have to use more than one PLC. Simulating the individual discipline-specific aspects also requires computing power, and it needs more computing power than the platform. The simulation platform actually is only used to calculate and display the energy and power values. By linking via OPC UA, it is possible to use different computers for every task. Only everything that is to control by controller should be on one computer if you are using a central PLC. Alternatively, values from the controller can also be transferred to the OPC UA server, and the server can distribute it to all tools. The last slide can be seen as a summary because within the system integration, the three disciplines, mechanics, electrics, and software, are linked, and the PLC program is tested. We call it virtual commissioning. The virtual commissioning is a tool that is used in the digital factory. It's assigned to the planning of production plants phase and thus take place before assembling. It refers to the commissioning on a virtual machine model that represents the mechanical, electrical, pneumatic, and hydraulic functionalities of a mechatronic plant. There are three types of virtual commissioning: model in the loop, software in the loop, and hardware in the loop. And the testing is always performed on the model, not on the real existing plant. The aim is therefore to model the model as realistic as possible. The terms model, software, and hardware in this context refer to the form of the control that is used here. Control within the model, control by a simulated PLC via PLC Sim Advanced, or using the control as a hardware component. At an early stage of the product process or development process, simulation by model in the loop can be used. The sequential control is inserted directly into the physical model, and everything is tested within the model. This is a more of process accompanying simulation, since individual steps are successively taken over by the control system. At this point, however, the physical plant model is already used, which is also used in the other two forms of virtual commissioning. Because in a further step, when the software engineer has already worked a great step, the control program can be tested on the simulated control in the model, and compared to hardware in the loop, this has the advantage that the entire periphery input-output modules does not yet have to be defined and modeled. Because if the real controller is used, it is necessary to simulate the whole periphery with Profibus connection, for example. The advantages of using virtual commissioning is to shorten the commissioning process in order to do parallelization, in order to do more tasks at the same time. You can also test the critical functions without having danger to destroy the real plant. Because of doing the tasks or the commissioning in advance, you can reduce the costs for improvement directly at the customer, and you can do the programs better due having less time pressure. As the presentation showed, co-simulation or distributed simulation can be used not only to simulate different aspects of the plant in different environments and tools, but also can be used to perform virtual commissioning. Plant simulation in this case offers all prerequisites for virtual commissioning according to software in the loop with PLC Sim Advanced. Certainly, there are still many aspects that can be improved here. One step that we are currently working on is to perform the simulation of electronic engineering components with MATLAB, and with MATLAB adding another tool to the co-simulation. If you have any questions, please do not hesitate to contact me or to ask them now. Thanks for your attention.